Great. Yeah, great idea. Okay, so what we're trying to, actually, let me zoom in a bit more. What we're trying to accomplish here is starting from this fact that this nice expression is equal to this infinite series for any value of x between negative and positive 1. Starting from that, we want to produce the fact that this series converges. So that series is nowhere to be found in the coefficients of what we have, but perhaps if we manipulate it a little bit, we can cause those coefficients to appear. So we need the reciprocals of the numbers like 1/3 and 1/4 and 1/5 to appear, and we need those to appear twice so that they multiply together and become the squares. So one way that I can see how to do that is what if we were to, well, the first thing I thought was, what if we were to take the derivative of both sides, right? If we were to take the derivative of both sides, don't worry about what happens over there. On the right side, we would get 0 plus 1 plus 2x plus 3x squared and so on. And so we do have these new coefficients now that have all appeared, but they're all in the numerator, right? We need them to be in the denominator. So rather than taking the derivative, we'll take the antiderivative. So let me go back here. So if instead of doing that, we were to take the antiderivative of both sides, like that, well, then it would be the antiderivative of what we have there, right? It would be, well, that term would become a x, and then a plus 1/2 x squared, and then a plus 1/3 x cubed, and then a plus 1/4 x to 4, and so on. Now I left a bit of a space at the beginning because there's also a plus c. Now, yeah, I'll just leave it as plus c, right? That plus c could be anything. So we'll have to watch out for that. Now on the left-hand side, we can actually take the integral. Actually, you know what? I'll leave that on the left side. It doesn't matter which side you put the plus c on. I'll leave it on the left side. On the left side, we'll actually take the integral, which would be, let's see, negative natural log of 1 minus x. If I'm not mistaken, right? Because when we take the derivative, it would be negative 1/1 minus x times negative 1. That's right.
Hey,
okay, so
we're texting in the group chat saying that they're not let in to the TA session. I don't know.
Oh, thank you. Okay, everybody should be in now. Sorry about that. Okay, so that's step 1. But unfortunately, we still have the sum of the reciprocals here, but we don't have the sum of these squares. So let's see what this would tell us. It does tell us something kind of interesting. It tells us that, you know, at this point, we can plug in any value of x that we want, and it will tell us something or other. If we were to plug in x equals 1, here's what it would tell us. It would tell us that, I mean, x equals 1, it would just become 1 plus 1/2 plus 1/3, that's 1/2, geez, plus 1/4, and so on, equals negative natural log of 0 plus c. Now, of course, natural log of 0 is undefined, but it is approaching negative infinity. So negative natural log of 0 is approaching infinity. So that makes sense, right? The sum of the reciprocals of the just regular whole numbers diverges. So it kind of makes sense that we get infinity in that case. But we don't care about that series. We care about the one where it's these squares. So you might think that we should take the integral again. But if we just take the integral again right now, the wrong thing happens. Right? This becomes 2 times 3. And this becomes 3 times 4. And so that's not quite right. Right? We needed this to give us another 4. Instead, it gave us a 5. So the trick is exactly what I think Kayla said earlier, that first we can divide both sides by x. And so we get this this function. Now it's still left at c. We'll have to think about that in a minute. but it's probably not going to matter. Because after we divide by x, we end up with this. And so now when we take the integral again, not looking forward to that. We'll leave that for a second. Equals, so the integral over here, that would be another, so yeah, we're gonna get another constant, so I'll call that d or something. But on the right-hand side, we end up with x plus 1 over 2 times 2x squared plus 1 over 3 times 3x cubed, right? So here we're ending up with the correct coefficients. And so now if we were to plug in x equals 1 to this side, it would be precisely the series that we are looking for. So we just got to make sure that when we do this and plug in x equals 1 to that left-hand side, it works out to be finite, right? Because that's what we're trying to show, is that it's finite. So let's see what happens here. Okay, so this right here. So I'm probably going to say wait a second. I'll probably say let u be 1 minus x, and that means x is 1 minus u, and it means du is negative dx. So this first integral here, which was negative natural log of 1 minus x over x dx, is now the integral of negative natural log of u over 1 minus u. See, that's not useful at all. That was terrible. Du, well, that will just get rid of that. Does anybody see how to integrate this?
Yeah, I typed it into an integral calculator earlier, and it said it's like a special thing called like a dialogarithm or something. And it's like Li sub 2.
Oh my gosh.
And I don't know what that is. That's why I was like, I have no idea what to do.
Well, that's not good. Is it really? It's like a transcendental thing. Well, that's crazy.
You can type it into integral calculator and see. That's what I did.
Nah, what am I trying to do? F of w dw dt. Wow, look at that. So that's what it looks like, the second antiderivative. But supposedly it's inexplicable, indescribable in terms of elementary functions, according to this person. Yeah, no. No. There's a, let's check if this is correct. What was that? C1 plus C2, x minus 1 log 1 minus x. Okay, I'll say x plus 1 minus x, ln of 1 minus x. What? Oh yeah, no, there you go. That's exactly right. So this is not indescribable. We must have just made a mistake here. That's not good. The derivative of that would be ln will be 1 over 1 minus x times negative 1, which would be that. Okay. Oh, because it's not the second derivative. I'm dumb. Because it's the because I forgot about this, the division by x. Okay, super cool.
You just broke the internet.
Yeah. Okay, so I actually should have done this. And it's not that. All right, so that changes it. Man, not sure why that's not working. Yeah. So I'm not sure what you're supposed to do here then, if that's if it's this specially named thing. Maybe the point is just that it's finite and that it converges and everything. But why? But how should you know that that converges unless you know?
If you look that thing up, it gives you like a series. It's like there's like a definition of it. It's like a, I don't know. It's like x to the k over k squared. If you look up like the Li2 thing, that's, I mean.
Well, right. I mean, sure, right. I'm glad it is x to the k over k squared, because that's exactly what we've
Yeah, and then you plug in 1 for x, and that's 1 over k squared. But like, I feel like what was the point of doing all that work if you can just say, like, from the beginning we could have said it converges by p series or integral test or whatever. Like, why do we have to compare it to the 1 over 1?
Yeah. Well, okay, so I guess this turns out to be this strange function Li2 of x, and then plus this would be c ln x, and then plus d would equal this series. And then indeed, if we plug in 1 for x, we would learn that the series that we are interested in, if we plug in 1 for x, we'll learn that the series that we are interested in is equal to whatever you get when you plug 1 into this function plus c times whatever you get when you plug 1 into this function plus d. Now that's 0. The question is this, and this is constant. The question is that constant or is that infinite? And you probably don't know because you've never heard of that function before in your whole life. So yeah, so I'm not really sure how that's supposed to elucidate anything. We can look up this function, or well, we've already got to have a graph of it here, don't we? And you can see that Li of 1 seems to be a well-defined thing. It seems to be like, I don't know, whatever that value is right there. It's interesting that it seems to be undefined right past that. But yeah, Li of 1 appears to be defined at least in the limit. So, and that's all you need. So yeah, so I'm not really sure what else to say about that. If it literally comes down to a function which you cannot integrate except by giving a name to the answer, which is all this does. You know, they're just calling it Li2, but and they're calling it that because there's simply no other way. There's no way to express this function in terms of simpler functions, you know, combined together. So they just had to call it its own thing. But it's not clear to me how that really explains anything or helps you in any way, you know. So yeah, so I'm not sure what else to say about this one. It turns out that this is finite because d is finite and Li2 of 1 is finite, which you know somehow. So therefore, the sum that you are seeking is finite. What do y'all think? Sorry, that was probably super disappointing. I'm not sure what else to tell you.
I think I agree with Kayla. I think, excuse me, sorry.
Why have to do all of that when it literally gets proven with p-series and integral test?
Well, that's also a really, really good question. Yeah, I really don't know what to tell you about that either. There's a lot of great questions that I couldn't tell you the answer to, really. But yeah. Okay, let me check the chat here. I hope I haven't been ignoring it. Glad you're liking it, Lauren. You're cool. All right. Anything else I can help you with? I'm sorry that wasn't super great. Anything else that possibly we could talk about? Can you guys see me still?
Yes.
Oh, okay, good. That's weird. I can't see myself anymore. Oh, there I am. All right, what's next? Anybody have anything? Can we go over some of the homework problems? Of course we can, right? If you wouldn't mind telling me the problem, that would be great. And then we will go through it. I hope I'm not missing anything when it comes to this. When it comes to this one, you guys, we're talking with the professor, and you think, and do you believe that this is the intended route? Kayla? Okay, I'll be back in a minute. If there's a problem in the chat, then we will go over that.
What are you doing, Kat?
All right. Any problems that you'd like to go over? Nobody put anything. There's 13 people here, which I'm happy to see, but I can only help you with what you tell me to help you with. Oh, sorry, Ryan, I don't see it. Oh, perhaps did you mean you sent it to me like in a different place? Okay, hold on.
I see it in the chat.
What the heck? That's weird. Really?
I can try to download it and send it.
What the hell? That's weird. I'm sorry, I can't see it. That's bizarre. Well, would you mind typing it or saying it? Sorry, I don't know why I can't see it here. That is weird. Oh, okay. Right. Okay, got it. Okay, so let's talk about this. So we want to know if what is it probably starts at. Actually, I have no idea. Does it start at 0 or 1? It really doesn't matter, actually. It really does not matter. Right? Because what happens in the first 1 or 2 or 5 or 10 terms is insignificant to the question of does it converge or diverge. Right? What happens is, you know, it really comes down to what happens in the infinite tail of the series. So to give a bit of insight, imagine you have a series which is like this, like it's like 1 plus a
You
third.
showing your whiteboard, John?
No, I'm not. Thank you very much. Right. So here's the series that we're talking about. So suppose you have a series which is like this, and the terms are getting smaller and smaller by some pattern. I don't know what the pattern is or what the series is, but imagine that like in the limit, the terms have reached like a final size, a final non-zero size. Let's say they are each worth 0.02. So what I'm saying is, what if the terms of this series, imagine that they approached 0.02 such that at the end of the series, you're just adding 0.0202 over and over. Well, I hope it would make sense that such a series, if the terms are approaching 0.02, would surely add up to infinity. Because in the infinite tail, you're adding together an infinite number of non-zero numbers together, and that's not going to be finite, right? Well, I say that it's very, English is very hard to say these things precisely. So what I mean is that in the limit, the terms get no smaller than 0.02. So you are adding together an infinite number of numbers which are all bigger than some limiting non-zero value, which means the whole series is going to be like a bunch of those put together, and surely that's infinity. The only sorts of series which do have a shot of converging are series like this one, where the terms are getting smaller and smaller and smaller without bound. So that in the eventual tail, it's not like it's like you're simply adding zeros together, because that's what the terms are approaching. Series like that do have a shot of converging, right? Now it's only a shot. Some series that are like that, as you well know, despite the terms approaching 0, right? These terms are approaching 0, and still that's infinity, because while they're approaching 0, they're approaching 0 too slowly. So yeah, so that's not a super powerful thing to know about, but it at least tells you what I'm saying is, if you look at the terms of the series and they're not approaching 0, if they're approaching some finite finite non-zero value, then the sum of all of those certainly diverges. Now that fact is called the divergence test. And it simply says, if the terms, well, let me say it differently. If the terms do not approach 0, then the sum of all those, and again, starting at 0 or starting at whatever, it doesn't really matter, of those terms is infinity. Now, if the limit is 0, then as you have seen, it depends. So we say the test is inconclusive in this case. So the divergence test is simply the fact that if you add together a bunch of things which are not approaching 0, then they definitely add up to infinity. So a quick test that you can do on any series is check to make sure that the terms actually approach 0, to see if it even has a shot of converging. But we see these terms the limit of these terms is 1/4, right? And you can quickly see that because the is a third degree polynomial on top and a third degree polynomial on bottom. So since they're the same degree, you simply need to compare the leading coefficients. And that works out to be the limit. The other way to see would be to do this thing where you multiply the top and bottom by 1/n³. And then you can take the limit, and definitely that goes to 1/4. So yeah, so this series is this kind of a series where it starts off, we can plug in 0, we'd get 0. You can plug in 1, you'd get 5. You can plug in 2, you'd get 8/33. You can plug in 3, I'll stop here. You'd get you'd get 27/109, and so on. But in the end, it's just like you're adding together a bunch of 1/4s, because those terms get closer and closer to 1/4 as you go along. So you can imagine that the infinite tail behaves like this, because that's what those terms are approaching. And since they're not approaching 0, they're approaching 1/4. Well, if you add a whole stack of 1/4 together that never ends, that surely is infinity. In other words, I'm saying this series diverges by the divergence tests.
So how again did you determine it approaches 1/4?
So so something like this. So you want to know what's the deal as n goes to infinity on that thing. So if you were looking at this for the first time, you might the problem is you plug in infinity into here, you plug in infinity into here, and it's infinity over infinity. So one way to handle this situation would be to use L'Hopital's rule. If you were to use L'Hopital's rule, is that familiar to you guys? It is, right? Then you would get it that way. That's one way to see. Another way to see is to do this trick to the top and bottom. Give it one of these. And if you do that, then you will get the equivalent expression 1/4 plus 1/n³. And now that it's in this format, now when we plug in infinity, it goes totally differently. When we plug in infinity into this term just disappears, and so it becomes 1/4 in the limit. That's another way that you can see that's the situation. Did either of those convince you?
Yeah, I think so. Well, how do you know to multiply it by 1/n³?
Well, just because the thing that I'm trying to prevent is when I plug in infinity in for here and in for here, I get infinity over infinity, and I don't know how to handle that without another technique. So if I'm just trying to use algebra to get the limit into something I can handle, then I'm going to need to get, it needs to stop being infinity over infinity, because I don't know what that is. So the numerator, if I were to do 1/n³, well then that would just be gone. And then same thing for this one, I would do 1/n³. Then the leading terms, the terms with the most n's in them, now just become constants, and then everything else goes to 0 instead. So with a more general example, like let's say 13n⁷ plus 4n³ minus 3n² plus 1 over 5n⁷ plus 4n⁴ minus 8, right? If I wanted to know what's the deal as the limit as n goes to infinity of this, one way to see the answer would be to say, well, the problem is if I just plug in infinity, this is 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 infinity, that's no good. I don't know how to handle that situation. So what I need to do is multiply by something or other, just get rid of some of those n's in order to work this out for real. So if I just get rid of a single n though, that's not going to be enough, right? Because this leading term would still have 6 n's in it. This one would still have 2. This one would still have 1. And then this one would now be 1 over n, right? So now when I plug in infinity, I know how to handle this one. So that's cool. But these are all still untenable, right? So what you ought to do is multiply by the 1 over n to the highest exponent around, 1 over n to the 7. And that way it will cancel from every term completely, including the leading term. Let's see, well, 3 of them would cancel on this one, right? So there'd be 4 left. Whoops, let me say that again. There'd be 4 left on the denominator. This would be minus 3 over n to the 5 plus 1 over n to the 7. So after having done this, which is just one thing that we could have done among many, many different things that we could have done. But having done this, now when we plug in infinity, this is 0, this is 0, this is 0, this is 0, this is 0. And these terms are totally understandable. So we can see that this limit in this case is 13/5. And so with a bit more experience, rather than doing all of this like algebraic work and everything, with a bit more experience, you can see a rational function like this, where it's a polynomial over another polynomial of the same degree. And you might just immediately know that the limit as n goes to infinity of that is going to work out to be 13/5, right? The ratio of their leading coefficients. And it's like that every time. And so even for something like this, where to go here? If you were just looking at this, you could be like, okay, well, that's 1 on top and 4 on bottom. They're both n cubed. So when you take the limit, they sort of, it just works out to be the same, this ratio of their leading coefficients. And is like that every time. Does that make sense?
Yeah,
Or does
that makes sense. Does this method work with most kinds of series though?
Well, only if it's a, so you can only take the limit like this when it's a, when it's, using what I'm, with the things that I've been saying. I'm talking specifically about polynomials over other polynomials, right? So if it's not like that, then, it's a totally different situation. And also I'm only talking about the divergence test, right? So this divergence test, let me put it in thing here. Sometimes it's called the nth term test. That's another name for it. It's literally the simplest of all the tests that there are. It says just quickly check that the terms are actually approaching 0. If they are approaching 0, then it has a shot at converging. So you can continue to think about it. But if the terms are not approaching 0, then it has no shot of converging. So it definitely diverges, and you can just stop right there. And you don't have to do any more sophisticated reasoning. You just take the limit, and if the limit's not 0, then it diverges. So yeah, so for a series such as this one, where the terms are of the form polynomial over another polynomial, and I observe that the degrees are the same, then I know that the ratio of that is 1 over 4. And since it's not 0, then that is a divergent series by the nth term test. So you can pretty much use this technique for any series where the terms are a polynomial over another polynomial. And if that works out to be infinity, or if it works out to be not 0, if the limit is not 0, then it definitely diverges. Another example would be, let's say, if it was a series like this, you could try the same test on it. But if you try to figure out the limit in the same way, right, you have to give these each a 1 over n squared. And so notice what would happen is that the numerator is completely out of constants, and only the denominator has a constant left. And so when you plug infinity in, all these terms are 0, And so you get 0 out of 4, and so you get 0. So according to the divergence test, these terms they actually are approaching 0 in the limit, which means it's possible, not definitely, but it's possible that this might converge. The nth term test alone cannot tell you that. But yeah, but it can tell you that since the terms go to 0, then it's got a shot at converting. Okay. It doesn't say where it starts. Well, great, because yeah, it actually does not matter where it starts. Okay. I hope that answered your question, Ryan. Or whoever else was asking me there. Are we ready for something else? Can we go over an example that uses the root test? 100%. 100%. So, hold on a moment. Okay. So the root tests. Right, so it's when you have a series, sum of a bunch of terms, right? The root test says find this limit. The limit of the nth root of the absolute value of your terms. So absolute value, just ignore whatever weird negative stuff's going on. Just ignore that, and then take the nth root. Of course, 1 over n is another version, another way of saying nth root, and that's why it's called the root test. So you take this limit, the limit of the nth root of your terms, and this tells you if that limit is bigger than 1. It's definitely going to be a positive number, right? Because we took the absolute value here. So it's surely going to be a positive number. If that is bigger than 1, your series diverges. If you take the limit and it works out to be smaller than 1, then it converges. And if it's exactly equal to 1, then it's inconclusive. So this test is not powerful enough to tell you what's going on if the limit is 1. When I say converges, I should actually add converges absolutely, which is a slightly stronger thing to say than just saying it converges. It means that even if you take the absolute value of the term, it still converges, right? So some series are like, some terms are positive and some terms are negative, and so they partially cancel each other out. And so they converge, but only because their terms are canceling each other out. And if you were to make those terms all positive, they would add up to infinity and it wouldn't converge anymore. Converging absolutely means that it converges so hard that even though its terms are negative and some of them are canceling out, you could flip them to positive and it would still converge, right? That's what it means to converge absolutely. So anyway, yeah, so this root test has 3 possible outcomes. It can tell you that it converges or diverges, or it can fail and say, I don't know, and you'll have to use a different test, right? So for example, I'll do a stupid example first. Let's say you want us to know whether this series converges or diverges, right? You could use the root test. You could take this limit as n goes to infinity of the nth root of the absolute value of 1 over n squared, right? But that's quite a hard limit to take, right? What the hell is going on, right? That 1 over n just adds this like weird complication, and it's not really useful to do this because I have no idea how to take this limit. Or maybe I can with some clever technique, but like this 1 over n thing is going to be hard to handle. So this is not an example where you would want to use the root test. An example where you'd want to use the root test would be something like this. Something like that, where your terms are blah, 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 to the power of n, right? Working with stuff to the power of n is quite challenging, because like if you're plugging in like 5, this would be 3 times 5 to the 5 plus 1 over 4 times 5 to the 5 minus 18 times 5, all to the power of 5. And that power only gets bigger and bigger as your terms go along. So it's really perhaps quite hard to understand what's going on. But the root test is literally perfect for this application because it says, find this limit of your terms those are your terms, the absolute value of the nth root of that. So low key, the absolute value, don't really worry about that because in the limit they're positive anyway, so it's fine. So the thing is, the nth power and the 1 over n cancel each other out, right? So you only need to find this limit, which is far, far easier without that big power of n. Right, in fact, this is exactly the type of polynomial over another polynomial that we have been discussing in the previous problems. Perhaps you know by now that that limit is for sure 3/4, right? Because they are the same degree. And so in the, whoops, I meant to put n here, but it doesn't actually matter. They're the same degree. And so the limit is just going to be the ratio of their leading coefficients. So yeah, so the root test produces this L of 3/4. And according to the root test, that means that this series converges absolutely. So the root test has concluded that this series converges. So of course, the thing that should trigger you to try to use the root test is when you have a big power of n, the whole thing to a big power of n. It's quite easy to use the root test if you have a big power of n to cancel out the the root. So yeah, that's the situation. You don't exclusively have to use it that way. You can use it in other circumstances if you wish, but it's usually inferior to other tests in other circumstances. So yeah. Okay. I'll go to 3 if you wish. We have time for perhaps one more problem. I hope that was explanatory for the root test. Let me know. Anybody have another one? Awesome. Awesome. So for the philosophy-minded folks, the root test is basically asking. Oh no, wait, that's not true. No, I'm thinking of the ratio test. Never mind. Never mind. Now wait a second. I don't know. Lauren says, I'm embarrassed to say 100 with telescope machines 2 to infinity of 2 over n squared minus 1. Don't be embarrassed. That's fine. So let's take a look at that. So yeah, so they kind of tell you that this is a where the hell I don't see how they get the final terms in using partial fractions. So sorry, do you mean to say you don't understand how to partial fraction decompose that expression, or do you mean to say that once you have done something after that?
No, I get how to do the partial fraction. Where I get lost is, okay, so you did it, you found your terms, you started telescoping, but then at the end, what the book was, because this is one out of the book, the answer is like 1 over n minus 3 minus 1 over n plus 1 over n minus 2 minus 1 over n plus 1 plus 1 over n minus 1 minus 1 over n plus 2. I don't understand how they get to that, because when I do it, I end up with 1 plus 1/2 minus 1 over n plus 1, and then go to take the limit from there. And that's clearly the wrong answer according to the book. So I don't understand how they get that.
Is there actual final numerical? It convert. Yeah, it does converge. Is their actual final answer different from yours?
Yes.
Okay. Well, okay. 2 over n squared minus 1. So what is the partial fraction decomposition of that?
So for partial fraction that I got, you get 1 over n minus 1 minus 1 over n plus 1.
Okay. Let's plug in a couple n's to see if I believe that. Let's say n equals 5. Is 2/5? Is that the same? Is that really the same as 1/4 minus a 1/6? I don't think so. Is it really? No, it can't possibly be. Wait, that's not 2/5. I'm stupid. N, what did I plug in? N equals 5. So n equals 5 would be 2/24. Aha. Yeah, that's correct, isn't it? A quarter, that's 3/12 minus 2/12 is 1/12. That's right. So this looks correct to me. This looks correct to me. Okay, great. So having done the partial fraction decomposition of this, I'm glad you figured that out without me. Or I'm glad I didn't have to right now, I mean. We can look at this sum. So I'm guessing it was probably from 2 to infinity of 2 over n squared minus 1. It's actually the sum. Same exact sum as this. Nice that they put that 2 there. Otherwise, 2 in the numerator there. Otherwise, we would have had a fraction here, but that's fine. Okay, so let's see if that works out. Okay. So first one, n equals 2 would be 1 over 1 minus 1/3. 1 over 2 minus 1/4. 1 over 3 minus 1/5. Right, these are the terms for n equals 2, n equals 3, n equals 4, and so on. Indeed, this is what I got when I plugged in n equals 5, right? So yeah, that's absolutely right. So I'll stop there. Actually, I'll go one more. Right, so that's what the terms look like for n equals 2 through 7. And of course, they keep going if we're trying to find the infinite sum. But let's just imagine we try to find the finite sum. I'll use a capital N to refer to the final term. So the final term, if I wanted to write that one, would be capital N minus 1. So capital N is short for 100 or 1,000 or 1,000,000 or whatever I'm choosing to be the last term of my finite sum. It'd be that. Now, personally, I'm quite happy just leaving it like that and just not worrying about the terms before that. And I'll say, okay, so here's what's going to happen, folks, is that cancels with that. That cancels with that. That cancels with that. That cancels with that. In fact, all of these are going to cancel. And I just say that cancels with that, and that one's the last one. But actually, I'd be wrong. I would be missing something quite important. Notice how on the front end, there's two terms. The first part of the first two terms don't have partners to cancel with them, right? And in the same way, we would be missing out on not just the last part of a term here that doesn't get canceled, but the term before that would also have a part that doesn't get canceled, and we would be remiss to not include that. So let's be careful. The term before that, the term before this one, right? Well, it would be those two, same two things, right? Same two numbers like this one, 1/5 and 1/7, like this, with those numbers shifted down by 1, right? So the term before that would be those same numbers shifted down by 1, like this and this. And the term before that would be those same numbers shifted down by 1, like this and this. And so indeed, everybody's going to get canceled out except for these last two, right? This gets canceled with this. This gets canceled with something in here. This gets canceled with something in here. And everybody cancels out except for those first two, guys circling green, and these last two guys circled in green. So yeah. So this is
So basically we're saying because you have those two terms at the beginning, you have to make sure that you shift down by 1 at the end to account for the fact that there's those two terms at the beginning.
Yeah, I'm saying the way that there were two terms that didn't get canceled at the beginning, at the front end of the telescope, suggests to me that the same thing will likely happen at the back end of the telescope. So I would be, my inclination would be to just write this one next to the ... But that would be wrong, because you really got to write at least two next to the ... to see that there's two terms at the end that don't get canceled, same way as the front end.
Okay.
Now, in the case of some telescoping series, what's the deal with these back two terms? This backs were 1 or 2 or 3 terms. In this case, it's 2 that don't get canceled. In this case, they both go to 0 as n goes to infinity. So really worrying about them is kind of not really a big deal anyway, because they both go to 0. So what I'm saying is, here we have an expression for the nth partial sum. If you add these all the way up to some capital N, it turns out it's 1 plus a half minus 1 over, what the hell was it? N minus 1 over n plus 1, right? They're both negative because, they're supposed to be, sorry. Right, because the second term, yeah, exactly, there's supposed to be negative. So that means, for example, like the 100th term, I can instantly tell you that the 100th term, if you add up all those, it works out to be the exact same as doing 1 plus a half minus the 100th minus 1 over 101, because I can see from the telescoping situation that all those terms in the middle are going to cancel out, and it's just going to reduce to these 4 things. And that means then that what I'm really interested in, the full sum, is 1 over a half minus 1 over infinity minus 1 over infinity plus 1. And those last two terms are approaching 0. So it's really 1 plus a half is 3 halves. So hopefully that's correct. Let's take a look. Let's ask the computer. Hey, computer, pick a big number and then figure out what's the sum from n equals 2 to infinity, to that big number of 2 over n squared minus 1. And if you go up to 1,000 terms, it turns out it's 1.498. And if we go up to 1,000,000 terms, it's 1.4999. And if you go up really high, it's basically 1.5. So it looks correct that that series is approaching 1.5 as p goes to infinity. I don't know why I used B here rather than capital N like I used in the thing. And I call it capital N. But yeah. What do you think about that?
I mean, it makes sense. So I guess like it's just a matter of accounting for the fact that you have multiple terms in the beginning. So if you have multiple terms in the beginning, you have to have multiple terms at the end. Is that like that threw me for a loop when I was working that problem?
Yes, you have to pay attention to multiple terms at the beginning and pay attention to multiple terms at the end, because the telescope doesn't collapse totally cleanly into one thing at the beginning and one thing at the end, right? It kind of has this staggered situation where it's two things at the beginning and two things at the end. But in the case of this particular telescoping series, those two terms at the end both go to zero. So even if you even if you forgot about this one, for example, you should get the same result. That it would be only it really just comes down to those first two terms.
Okay, cool. Thank you.
Okay, all right, you are welcome. This might be stupid. At the end terms, why are you adding it inside? Oh yes, because that was a mistake. Thank you. Right. Okay, anything else I can help anybody with? Or we'll stop there. I do enjoy talking about series, so I don't mind at all. All right, then I guess we'll stop there. Thanks everybody for coming. Good luck with everything. When is your? Can anyone tell me when's your upcoming? When is your exam 3?
Quiz on the 23rd, test on the 30th.
Damn. Okay. Oh wait.
Quiz on Tuesday and then a test the week after.
What's on Tuesday?
Just a quiz.
Ah, okay, sorry. Gotcha. All right, thank you. All right, so the 30th, gotcha. Okay. All right, everybody. Nice talking to you today. Have a great one.
Cheers.
See you next week. Bye-bye. Stop recording.